Hi guys, and welcome back to my channel. In this video we're going to be discussing solid-state chemistry, a very brief introduction to solid-state chemistry focusing on metals. And essentially in this video we're going to be attempting to describe the properties of metals that we observe with their electronic structure. And specifically, the theory we're going to be using is band theory. And you might have heard this from AP Chem, but you've probably described it just as a very surface level understanding, just saying that band theory is, or metallic bonding, is just a sort of like a bunch of nuclei with a sea of electrons that goes back and forth. But that's not very descriptive, and I want to give a little bit more, a little bit more understanding to you guys on what band theory actually means. Okay, so let's just go over some very brief, introductory stuff. What is, the ability to carry electric current can be separated into two sort of distinct groups. The first is electronic conduction, and electronic conduction is where we have electrons as the charge carriers. That should make sense. We also have ionic conduction, which is where we have ions as the charge carriers. So for example, like if you say a sodium chloride solution is conductive, right? That's ionic conduction. Electronic conduction would be more like something in a metal, right? Where electrons are actually moving. Okay, and we have these sort of classifications of different materials. And essentially, all that they differ by is how the resistance changes with temperature. So an insulator, right? An insulator, we have insulators which don't conduct electricity at any temperature, right? We have metallic conductors, and these are electronic conductors. So metallic conductors are electronic conductors, right? So metals, like a piece of wire, for example, when you put a current through that, that's electrons that are moving in the wire and carrying the charge. And with metallic conductors, when we raise the temperature, resistance goes up, okay? So, and this is actually because, for example, if I raise the temperature in a certain metal, what's going to happen is these nuclei, the nuclei of the metals vibrate more and more. And when these electrons sort of bump into the nuclei, they get like scattered. And because of this, the actual movement of electrons through the metal is much more inefficient and slower. And that's why your resistance is going to go up. So it's kind of a weird notion, but in a metallic conductor, you're going to have resistance go up as temperature goes up, right? And you might have heard of like superconductors. When you lower the temperature to really, really low, when you go like a few degrees above absolute zero, now there's research being done on high temperature superconductors. But generally, you go to really, really low temperatures, your resistance is going to drop, and you end up with this phenomena called superconductivity. But essentially all I wanted to say was metallic conductors, you have temperature up, resistance up. With a semiconductor, on the other hand, these are also electronic conductors. But when the temperature goes up, the resistance goes down, okay? So, typically metallic conductors have much higher conductivities than semiconductors, but the actual distinction is between the temperature dependence. That's something important. Right, this is the actual distinction. Temperature up, resistance up with metallics, temperature up, resistance down with semiconductors. Then, as I just mentioned, we have superconductors, which are electronic conductors, but they have really, really low or zero resistance, and they're usually at really low temperatures, right, because they are essentially metallic conductors. Then there's also some solid electrolytes. And solid electrolytes are ionic conductors. They're electrolytes. So electrolyte solutions are like salt solutions, right? So they're ions. We're going to focus more on, the structure of insulators, conductors, and semiconductors. Those are the three interesting ones to us, and we're going to try and delve deeper into the molecular orbital theory behind them and the band theory that describes their properties. And just an interesting way, or of the way we quantify the conductivity, right? I told you very qualitatively what these conductivities are, but how we actually quantify that is using this, electric conductivity kappa, and it's defined as the length of a piece of metal divided by the area times the resistance. Basically, as resistance goes up, conductivity will go down, right? As length goes up, your conductivity will go up. And as area goes down, or as area goes up, your conductivity goes down. But yeah, this is just a formula. It's not super important. It's just how we quantify conductivity. All right, so now that I've given like a brief overview on all these terms, right, we're going to jump right into the molecular orbital theory that describes metallic conductors. Okay, so how can we describe this huge system, right? Within a metallic conductor, there's tons of these metal atoms that are stacked up next to each other, and all of these orbitals are interacting in some sort of way, and they're forming, different molecular orbitals. So how can we even begin to reason such a huge system? Essentially, all we do is treat these conductors as one huge molecule. And then we can apply like particle in a box type molecular orbital theory, right? So let's give I'm just going to give a very general overview. These valence electrons in the metal are going to occupy these delocalized orbitals, these delocalized molecular orbitals that are going to spread through the entire solid piece of metal. And an important thing to remember is that if we have n atomic orbitals, that's going to form n molecular orbitals. So if we just think about, how many atomic orbitals are in this entire solid structure of metal, that's a huge amount. So we're going to have the same amount of molecular orbitals. That's a huge number of molecular orbitals, right? So the number of these delocalized molecular orbitals are going to be massive, right? And another thing that's important is that compared to a small molecule, like we usually use with particle in a box, the length of the metal, right, is way, way bigger. And if we look at the energy in particle in a box, we derive the energy levels of the electron to be equal to n squared h squared over 8 ml squared. And this is in a previous video of mine. If you don't know a particle in a box, you should probably go watch that and see the derivation before this video. But these are the energy levels for a particle in a box. And if we see, we have length in the denominator, right? Okay, so if the length of the metal is much, much, much bigger, say when I subtract these two, right? When I subtract the n+1 energy from the nth energy, so this is the difference between two consecutive energy levels, we have 2n+1 times this factor of h squared over 8 ml squared. And because the length is so much bigger, that means this entire factor becomes much, much smaller, right? And that just says that the differences in energies are really, really small. Because this 2n+1 factor is, that's some constant that depends on what energy level you're starting at and what you're ending at, right? But this h squared over 8 ml squared is another constant. And because L is so big, that constant is going to be really, really small. And that's going to make this entire term really, really small, right? So the differences in energy levels are tiny, and there's a huge amount of energy levels. So what does that result in? That results in a nearly continuous band, right? So we have a nearly continuous band. And this comes from two things I want you to remember, right? Small delta energies between molecular orbitals and a huge number of MOs, right? So these are the two key facts that basically ground this band theory, okay? So on the right here, you can see this is an image of our energy on the left hand, on the y-axis, and we have, pictorial representations of the most bonding orbitals and the most antibonding orbitals. And you can see in the most bonding orbital every single atom, and this image is showing s orbitals. So we can see that they're s orbitals because they're spherically symmetric, right? They look like spheres. It doesn't look like a p orbital that has this dumbbell shape. It looks like spheres, right? So we're looking at s orbitals specifically in this image. But in the bottommost, in the lowest energy orbital, is going to have all of the different orbitals in phase with each other. And that's sort of this low energy, totally bonding orbital. And you can see that they're in phase because they all have the same blue, dark blue color. instead if we look at the most antibonding orbital, you see we have the most number of nodes, right? And what does nodes mean? That's where it switches from positive to negative. So you can see that we have this dark blue, light blue, dark blue, light blue. It keeps switching between every single atom. And between each of these atoms, there's a node because it switches from a dark to a light or light to a dark, which means there's a node in between. And that results in the most number of nodes, which results in the most antibonding molecular orbital. So, and in between these, we have a whole energy range, right? And this energy range is full of other MOs that have a node number that's in between the most antibonding and the most bonding. And this essentially is going to form some sort of continuous band, quote unquote. And you can see that we just draw it as just one huge band, right? We don't make the distinction between the energy levels because the delta energies are so small. And if we zoom in, that's being shown in this zooming in image here, you can see that we have all these different lines, right? And those are our tiny, technically discrete energy levels, but they're so close together that we just approximate it as a continuous band. That's basically where band theory comes from, is we have this band of molecular orbitals. Alright, so this image is just a really similar way of showing what I was trying to show on the previous slide. I'm just trying to show, here we have the energy level on the y-axis, and this is basically how we construct the MOs for metallic conductor. And on the x-axis, we have the molecular orbitals for different numbers of atomic orbitals that combine together. So you can see that, okay, if we just have one atomic orbital, obviously there's just one molecular orbital. Now, if we have two atomic orbitals that are combining, we're going to have one bonding and one antibonding, which you can see here. If we have three, we're going to have one bonding, one middle, one antibonding, and it keeps going, right? And it keeps going when you have more and more and more atomic orbitals. And you can see that this diagram shows, okay, now what if we have 30 atomic orbitals, right? And you can see that the energy levels are getting more and more and more scrunched together, right? So as the number of atomic orbitals increase, these molecular orbitals are becoming closer and closer in energy and are eventually, right, as I get more and more and more, they're going to look like this. It's going to look like an energy band. These energy levels are going to become continuous, and this is going to become a continuous set of molecular orbitals, which we call the energy band, right? And you can see, just as I showed in the previous slide, we have the bonding molecular orbital and the antibonding where we have all the nodes, and the bonding where we have 0 nodes, right? But there's a few things I want you to notice from this diagram. The center, if we look at this, say, if we look at the energy of the original atomic orbital, which is this guy right here where we have just one atomic orbital, that's our original atomic orbital that I'm starting with, right? And then I look at this band gap, right? The center of my energy band right here, if I look at that center, is going to be equal, to the energy of my original atomic orbital, right? And that should make sense because in total, right, my energies of all my molecular orbitals have to sort of average out to my energy that I started with, because I can't sort of create or destroy energy, right? So the energy of my atomic orbitals, or the energy of my molecular orbitals that I create, the energy of my band on average, the energy of my band orbitals on average, I should say, should be equivalent to what I started with, the energy of my atomic orbital. And another thing I want you guys to take away is that the depth of the energy band, right? What affects the depth of the energy band? And what I mean by the depth is how bonding we actually form. So what is deciding whether the bonding stops here, the bonding goes down to here, the antibonding goes here, or if the antibonding goes there, right? What makes the height or the energy, or basically, how do I determine how bonding the most bonding molecular orbital is? How low in energy is the most bonding molecular orbital? How high in energy is the most antibonding molecular orbital, right? And this is determined by the depth of the energy band, right? How low it goes, how high it goes. And what changes this is how diffuse the atomic orbitals are. So the more diffuse the atomic orbitals, the better overlap they're going to have with each other, right? They're going to have better overlap with neighboring atoms, and that means there's going to be more sort of bonding character, right? If there's more overlap, there's more bonding. And that's going to cause the band gap to be more stretched, right? That's going to cause this energy band to be more stretched out, like that. Say if it was a more diffuse orbitals that was coming together, it would be longer, like this. If it was less diffuse, it would be shorter, like that. So those are two important things I want you to take out from this diagram. Okay, so now I've talked a lot about bands, and now I want to clarify exactly what I mean by bands, right? I know I've previously sort of rambled on about bands. Now let's define the terminology a little more rigorously. First, we have a conduction band. And conduction band means that the band is empty or incompletely filled, right? That's what a conduction band is. A valence band is a band that's full, right? So if we remember, I showed that we have this energy band, and this is a huge amount of molecular orbitals, right? And depending on how many electrons are there, it can either fill some of the band, the entire band, or none of the band if there's no electrons, right? So just think of a band as just a bunch of MOs, and we got to think about what fraction of the band is actually full. Conduction band means 0 or partially filled, some fraction. Valence band means it's all the way full. And the band gap, right? The band gap is the range of energies for which there are no orbitals. And this is oftentimes the energy difference between the valence and conduction bands. So just to give an example, say we have this valence band down here that's all the way full, and we have this conduction band up here that is empty, right? The band gap is going to be this distance between the valence band and the conduction band, because all of this here in between these two, there's no orbitals, right? There's no bands. And that's why we oftentimes, it's the difference between the valence and the conduction bands. And the band gaps, right, this energy between the valence and the conduction bands generally defines the type of solids. So in a semiconductor, you're going to find that the band gap is not 0, but it's pretty small, right? It's relatively small because what can happen is temperature. We have a little bit of thermal energy, and that can excite an electron from the valence to the conduction band, and when the electron is in the conduction band, it is free to sort of roam around because that band is empty. With an insulator, you're going to find that the valence band is much lower in energy than the conduction band, and so exciting an electron from the valence to the conduction band takes a lot of energy, right? And that's not favorable. So it doesn't conduct electricity. In a metal, what you're going to find is the band gap actually overlaps, or the valence band actually overlaps essentially with the conduction band. So it's really just one conduction band, essentially. You're going to find that the conduction band, we have a conduction band that's only partially filled. And what that means is there's basically 0 energy to go from where the electron is to a conduction band, because it's already in the conduction band. It's already partially filled. So in a metal, you're going to find that the conduction band has some electrons, but it's not full because it is an incompletely filled band. And that allows metals to transmit electrons and sort of conduct electricity without any, major amount of resistance. So now I just want to talk about a little bit, period 3 atoms, and as we go down in periods and how that changes, the bonding that goes on in metals. So in a period 3 atom, or in any atom in general, we treat each type of atomic orbital as independent. So for example, we take 3s orbitals and we look at the molecular orbitals they create, and that's going to be similar to what we saw previously, right? We saw that when we have s orbitals all lined up, we have the most bonding being all of them in phase, the most anti-bonding being all of them out of phase, right? So that would be really similar to our 3s orbital picture. And we can also look at, 3p orbitals, and that's going to do a really similar thing and form another band, right? We treat each of these atomic orbitals as independent. So, the overlap of 3s orbitals are going to form energy bands, and the overlap of 3p orbitals are going to form energy bands. And so if we look at, an example, say we have aluminum. Aluminum has 3 valence electrons on each atom. So if we say there's n atoms of aluminum, we're going to have 3n electrons, right? Because each aluminum atom has 3n valence, or 3 valence electrons, so 3 times n is going to give the number of electrons total. How many orbitals do we have, right? We have each aluminum has 1 3s orbital and 3 3p orbitals, right? So we have 4 orbitals total. We have 4 times n MOs, because the number of atomic orbitals has to equal the number of molecular orbitals. And that means we have 8n spots for electrons, right? Why? Because remember that each molecular orbital can hold 2 electrons. So if we have 3n electrons, 8n spots, that means our conduction band is 3/8 filled. So this is just an example of how you would, see that, okay, aluminum has only a partially filled band. That's going to mean it's conductive, because the electrons occupy a conduction band. And when they occupy a conduction band, they're sort of free to roam around, because the band is only partially filled, and a tiny amount of electricity, or a tiny amount of energy, is going to excite the electron between these different molecular orbital states, right? So this is how we can see that the electrons in aluminum occupy a conduction band. Okay, so and why just to give a little intuition between why a conduction band is conductive, right? The conduction band being only partially filled means that the lowest unoccupied molecular orbital, or the LUMO, is essentially infinitely close to the highest occupied molecular orbital in energy, because they're so close in energy together. And this explains the ease at which electrons can sort of excite to these empty orbitals and conduct electricity and move throughout the solid, right? So because the HOMO and the LUMO are so close together, that's basically our band gap. Our band gap is equal to 0. And therefore, right, it's so easy for these electrons to excite and conduct electricity. But how does period 3 and below differ from period 2, right? 2s and 2p, for example. 3s and 3p energy, orbitals are going to be longer than 2s energy bands. So this is important. The 3s and 3p are going to be longer than 2s. And why? Because 3s and 3p are further out from the nucleus. They're more diffuse orbitals, right? And when they're more diffuse, that means we're going to have lower energy bonding and higher energy anti-bonding. I explained this in the previous slide, right? More diffuse means more overlap, which means lower energy bonding, more bonding. And that just means that these energy bands, so for example, if I drew them out, if we had 2s here, our band might look like that. If we have 3s, our band is going to be longer, right? So we're going to have a longer sort of energy band. Next, we also have that 3s and 3p, the original atomic orbitals, are much closer in energy than 2s and 2p, for example, right? And this is because they're both much higher in energy, and as you go higher, as your principal quantum number gets larger, your energies sort of get much closer together, right? And that's because you're going farther away from the nucleus and you're raising everything in energy. And yeah, so essentially, as your principal quantum number gets larger, your distinction between S and P gets closer in energy. So we have these two things coming together. We have the fact that our bands are going to be longer for 3s and 3p, and our original atomic orbitals are closer in energy. So if I drew this, let's draw this a little better. If I have an energy diagram, and we have, 2s, 2p there, and our bands are, fairly small, maybe. Whereas if we have, we have 3s and 3p, and our bands are much longer, right? What we're going to find is that these bands basically overlap. These 3s and 3p energy bands overlap, and they're just going to form one large band because they're both closer in energy and individually have longer bands than each other. And this is why with aluminum, right, we were able to take both the 3s and 3p and combine them into one, right? We just said, okay, there's 4 NMOs, because we could take 3s and 3p as similar orbitals when they combine, because they're very similar in energy and their bands are just gonna sort of fuse together because of this. Okay, so now I want to go back to, what are the properties of metals, the obvious properties of metals, and why can we now explain them using band theory? First, what are the requirements for metallic behavior? We have delocalized orbitals that lead to this band of energy levels, right? This is what we found with band theory. We have more and more atoms, more and more molecular orbitals that are, or more and more atomic orbitals that are, sort of overlapping and creating these mix of molecular orbitals that are infinitely close in energy together and form what we call a band, right? So we have these bands of energy levels, and we have metallic behavior when we have this band that's partially filled with electrons. And that means that it is a conduction band when it's partially filled with electrons. When we properties of metals, they're also electronic and thermal conductors, right? And why can we reason this now? Is that we only need a very small amount of energy to excite electrons to an empty orbital. Remember, because they're already in the conduction band, so the distance between the HOMO and the LUMO is really, really small. We need that tiny amount of energy, and after they're excited, they can then move around the metal and conduct this thermal or electronic energy. Next is that metals are very lustrous, right? And why are they very lustrous? Because lights of many different wavelengths can be absorbed and emitted. And why is this true? Because we have this huge range of different energies that we can jump between, right? And we can basically jump anywhere. Like if I drew a band and I have an electron here, I can basically jump to any different one of these energy levels. Like I can jump anywhere because there are levels at any different one of these specific energies, right, in this band. And because I can jump to basically any energy level within the band, I can absorb, this electron can absorb light at any different wavelength, or any of the wavelengths that agree with, these different energy levels. And because there's so many different wavelengths that I can be absorbed and emitted, the metal is going to appear lustrous. Finally, let's reason, the strength of metallic bonds. We have the strongest bonding when most of the bonding orbitals are filled, right? So if we remember with our bands, when we drew our bands, we have like an atomic orbital that starts at some, say this is the energy of our atomic orbital that we're starting with, and eventually we get to a band like this when we have a ton of these different atomic orbitals coming together. And anything lower in energy than this atomic orbital is called a bonding orbital. Anything higher in energy is going to be an antibonding orbital. The bonding orbitals are lower in energy, antibonding are higher in energy. So if I split this sort of in half, then these guys are going to be bonding, and the other half is going to be anti-bonding. So if I fill up the bonding to the maximum extent, that means I'm lowering the energy of my electrons to the maximum extent. Because if we think about how it was going to be before, like if I just had atomic orbitals and I had a bunch of electrons filling the atomic orbitals, they would all be at this energy. But now that I have bonding, and I fill it exactly halfway, all of the electrons are going to be below how they would have been before, right? So if I fill up all the bondings, that means I have this maximum sort of lowering in energy. I have the maximum stability. And that means that's going to result in the strongest bonding. So whenever we have the conduction band half filled, which is exactly what's happening here, we have the bonding, all of the bonding orbitals occupied and none of the anti-bonding orbitals occupied. That means these are going to have the strongest bonds, right? Because there's the most lowering in energy of the electrons. And this happens with metals right in the middle of the periodic table. So these metals right in the middle of the periodic table are going to have, right, the strongest bonding. And why is it metals right in the middle? Because if we go to the left, right, then not all the bonding orbitals are going to be filled. It's going to be like something like that. If we go to the right, we're going to start filling the anti-bonding orbitals. So it's going to look like something like that. Whereas right in the middle, we're going to have, a nice halfway point. All right, so this is basically all I wanted to talk about in this video. This was focusing more on metals, and in the next part of this solid state chemistry video, I'm going to be talking more about semiconductors and insulators, but it's all really the same thing, right? We're all just looking at the band gaps and seeing, what is the energy difference, what is the band gap, right? The energy difference between the conduction and or the valence and the conduction band. So, and that band gap basically defines the type of material it is. All right, thank you guys so much for watching, and I'll see you in the next one.